Okay, welcome everyone. Uh, Thank you all very much for staying to the end of the day for this talk. My name is Doug Hawkins. I work at Abzul Systems on the just-in-time compiler and related things around it. And this is a talk about Java performance. In the spirit of Josh Block's book on Java puzzlers, this is Java performance puzzlers. We're going to look at a few cases of some surprising performance outcomes where you think something should be faster and isn't faster, or there's a non-obvious compositional problem, or something along those lines. And it is worth saying that unlike most JVM developers, who actually don't write a lot of Java, believe it or not, we write in C++. I was a Java developer for 10 years first, so I've actually been on both sides of this. I've written genomics applications, financial service applications, e-commerce applications in Java. So I've done both. So the agenda is pretty simple. We're just going to look at some interesting and often unintuitive and sometimes funny performance cases and see what we can learn from them. Some of them will be serious, some of them will be, well, not so serious. Now we're going to start with a not so serious one. Okay, A, B, or C. Do you think it takes longer to add the numbers from 1 to 1395, 1 to 1396, or 1 to 1397? If you guess C, you are correct. It is going to take a little bit longer. But how much longer? Well, that's what we're going to find out. But how are we going to measure this? Measuring Java performance is actually pretty hard. If you came to my talk earlier today, you learned about all this JIT machinery going on, and it compiles methods at different times, and it's going to start slow, and then it's going to run fast later. And that makes benchmarking difficult. A typical Java program is going to go through something like this. It's going to start off running in the interpreter. It's going to take tens of thousands of nanoseconds to do the simplest of things, if it's doing it enough times. But after that happens for a while, you'll run in the first tier JIT, and things are going to get a bit faster. And if you keep running that piece of code, it gets truly hot, and the only parts of your system that matter are those that are truly hot, then you're going to get to the second tier JIT. And if your code didn't get to the second tier JIT, well, it just doesn't matter performance-wise. You might have heard you spend 90% of your time and 10% of your code. No, that is a lie. It's about 3% of your code. It's a vanishingly small percentage. And then it's actually possible for your code, once it's gotten to this optimized tier, to go backwards and go to the interpreter and run slow again. And then to C1, first tier JIT, and then to C2 again. And all this is going on underneath. And you can see just from looking at this chart, if I profiled at the very beginning, that's what I measured, I would get very different numbers for this particular one, where I'd get like 30,000 nanoseconds while I'm in the interpreter, versus it's actually only a couple hundred nanoseconds once it's in the second tier JIT. So you really want something to remove this for you. And the tool that we in the Java community have largely settled on is something called JMH, the Java Measurement Harness. It's basically a tool that lets you write micro benchmarks, kind of like JUnit tests. So you say, using annotations, how you want to measure. I want to benchmark them using average time. Tell me the time output in nanoseconds. If I got some setup code, I annotate a method with setup and put it there. Set up all my test data. And then I can annotate not with test, but with benchmark to actually have my benchmark methods. And then I can have a few of those so I can compare how long they all take. And then JMH will take care of running my code enough to make sure it gets to the second tier JIT and it truly is hot and we're really measuring the right thing. So let's see it. Let's check adding some numbers. Now, I've chosen to add the numbers in what we might agree is a non-optimal way. Here's my benchmark. If we scroll down, this is how I've chosen to add the numbers from 1 to 1395. Yeah, maybe a loop would have been better. Don't worry, I used a loop to generate this code. I know how to use a loop to generate code that I should have used a loop for. But we're going to see how long this takes. I'll let you imagine what 1396 and 1397 look like. To get started using JMH, you kind of have to use Maven. JMH is doing a lot of interesting plugging into Java-C under the covers, and it's just easier to get all that to work if you use the Maven archetype. Okay, there we go. It has built. I could choose to run the entire benchmarks jar. You do not want me to do that we will be waiting well past 6 o'clock. So instead, I'm just going to run one benchmark at a time using some scripts that I've already made. Oop. All right, by default, if I had not annotated my benchmark, JMH would be extraordinarily thorough. It would do 10 warm-up iterations. It would do 10 measurement iterations. And it would actually do 10 forks of the VM. And if I did that, this simple program, we would be watching the benchmark run for about 20 minutes. So I've cut this down to 2 forks of the VM, 2 warm-up iterations, and 5 measurement iterations. You're going to just have to trust me that that is not going to change the outcome much. All right, so here are our results. 1395 numbers takes 3.7 nanoseconds. 1396 numbers takes 3.7 nanoseconds. 1397 numbers takes 2680 nanoseconds. Wow, that last ad was expensive. What? That makes no sense. What happened here? Okay, so 3.7 nanoseconds is about enough to return a constant, and that's about it. And that's, in fact, that's what's happening here. When the just-in-time compiler gets a hold of this code, it goes, ooh, guess what? I'm really smart. 1 plus 2 is 3. Ooh, and 3 plus 3 is 6, and 6 plus 4 is 10. And it can actually pre-compute the entire result. And all it's doing is returning a pre-computed value once the just-in-time compiler gets a hold of it. So why couldn't it do that for 1397? Oh, it could. It chose not to. There is an arbitrary limit inside the VM about how big a method we are willing to just-in-time compile. And that is what we have run afoul of. Performance is full of surprising performance cliffs like this. In this case, there's what's called the huge method limit inside of the VM. At a certain size, we just say, no. What is wrong with you? And it turns out that adding 1395 numbers is about 7,993 bytes of bytecode. Adding 1396 numbers is 7,999 bytes of bytecode. And adding 1397 is 8,005. Would you like to guess what the huge method limit is? 8,000, yes. And that is the difference here. But there are all sorts of arbitrary things like this. I actually worked for a company where the hot method in the system was 7,900 bytes. Like, wow, that's getting scary. Oh, don't worry. The thing already took 150 arguments, and there's another arbitrary limit at 127 arguments, so that just wasn't getting jitted for like years. Okay, but this example is silly. Maybe we should just use a for loop. That would be a little more sane. And what number would we get? Then they're all nice and consistent, 435 nanoseconds. They're all consistently bad. They're 100-fold worse. But hey, there you go, nice and consistent. The compiler should, frankly, be able to optimize this, and it failed. Okay, let's try something a little more practical. I want to copy an array of integers. How might I do that efficiently? I could use system array copy. I could write a for loop myself. Or I could call array clone. As far as I'm concerned, this is the one acceptable use of clone. Okay, which might be fastest? Well, system array copy, have you ever looked at this thing? It's got the craziest signature I've ever seen. It takes object int, int, because the only parent type of all arrays is object. Should we have just overloaded the method? Probably. Did we? No. Well, that seems like it might be kind of hard to optimize. Maybe. On the other hand, it is native, and that sounds cool and fast. Okay, or I could just do this for loop and I get these nice strong types. Maybe that will be faster. Let's see. If we actually do this for an array of 100,000 integers, okay, they all turn out the same. They all come in at about 9,500 nanoseconds. That's not too bad. So it really didn't matter in the end. But you know what? I really want you to call array copy. I really, really do. It is actually faster under a particular circumstance. When the VM is starting up, yeah, this code is ice cold, but let's go ahead and make it fast if we can. I'm going to do a one-shot measurement in the interpreter. So in the top left, we are measuring doing a manual for loop. And in the lower right, we are measuring doing array copy using both with system nanotime. And if you run this program on this laptop, this is what you get. The copy loop is 2 orders of magnitude slower. Why? Well, system array copy, despite its crazy signature, is this thing called an intrinsic. We have magical knowledge of what it does. There is actually no code, Java code for this. It is inside the VM itself. And we will actually generate machine code optimized to the machine you are running on the very first time. You've got AVX 128, great, we'll use that. AVX 256, even better, we'll use that. AVX 512, well, those aren't out yet, but if you had one of those, yes, our VM would actually use that too. And you just get to have that. It's free from the very beginning. Eventually, it will get there with the manual copy loop when that code gets hot, but at the beginning, it's going to be slow. And performance is full of all these little intricacies. Your homework for tonight is to go find the list of intrinsics for the VM and memorize it. It's only about, I think, 270 today. And I'll come back and ask you all of them tomorrow. But one of the other things I want you to see from this example is, both of these are nominally order n. There's really no difference here from a big O standpoint, but clearly one has a slightly larger constant factor. And oftentimes when it comes to optimizing your code, it is much easier to do something that reduces the constant factor than it is to completely rewrite your algorithm from n squared to n log n. For instance, if your collection has a bulk put operation on it, like add all or put that takes an array on a buffer, you absolutely should call that. It is likely to be faster by a factor of 10. Okay, let's move on to something else. I want to take an integer, and I want to take an int, and I want to turn it into an integer. How might I do that? I could call integer value of, I could call new integer, or I could just, put the x in an integer context and it'll get auto-boxed. Which do you think is faster? Well, the answer is it depends. You can't get this one right, so. It is correct to say that A and C are equivalent. Auto-boxing is just syntactic sugar for calling integer value of. You could actually go and disassemble this with Java P-C, and you could see that for yourself. and hopefully you're willing to agree that if we give it the same bytecode as input, we should get the same result. The reason that you can't quite get this right, though, is behind integer value of, there's a cache. It caches the numbers from -128 to 127 by default. You can actually configure the upper bound. You can't configure the lower bound for some reason. And it's just an array. That's all it is. We pre-compute the array. There's no hashing or eviction or any of that. It's just calculate, index into array, return it. Super fast, super simple. How could this ever be slow? Well, let's see. To test this cache, we're going to need to parameterize our test. And JMH lets me do that. I can parameterize a test by just using a param annotation and telling it what values I want this variable to have. And then in my setup code, I can use that. So I interpret the value of 100 to be use the range of integers from -100 to 100. So that would always hit cache. -1,000 to 1,000 will hit cache some of the time. And then -10,000 to 10,000, well, okay, it hits cache some of the time, but basically never. And here are the results. If you did this with JMH, it would show you the range column. This is a little bit hard to read, so I put it in a nice table. Here you go. So new. New is very, very, very consistent because it's only doing one thing. It always comes in at somewhere around like 6 nanoseconds. Auto-boxed and value of, well, yeah, they are the same. When they hit cache, they're absolutely better. About 5 nanoseconds for the left column there. That's 20% improvement, or 15% improvement. Pretty good. But when they miss cache, they're actually worse. Even a simple cache lookup like that does impose about 10% overhead. In this case, I mean, this is a simple lookup and simple return, so don't take those relative values too seriously, but it is slower. But you see the really strange numbers here? Those 2 in orange. Why is -1,000 to 1,000 even slower still? Why would that happen? Because when we always hit the cache, the hardware will predict that we will always hit the cache. When we almost always miss the cache, the hardware will predict that we almost always miss the cache. Guess what happens when it's about 10% of one and 90% of the other? The hardware gets really confused. And so it actually goes slower, even for something as simple as this. Yeah, unfortunately in performance, every layer of the system matters, hardware included. So there's really a lot to absorb to try to get to the bottom of this. To take another example where the hardware has a strong influence, I just wanted to iterate over a list of integers, or an array of integers, or a linked list of integers, and see how long it took to sum up all the values. The blue line here is an array of ints, and you can see it's rock solid, very low, from 100 all the way up to, what's that, 1,000,000. Array list is the green line. It does sort of go sideways at 100,000 because of the amount of memory that the boxed integers are going to take up. And then there's linked list. That's the yellow line, if you were wondering. But all we're doing is iterating over some ints. It's all nominally order in. Why are they so different? Well, linked list is like this in memory. Everything you're putting in there is actually 2 objects, right? There's the actual integer itself, and then there's the node in the linked list, and that takes up a lot of space. And it's also just kind of jumbled in memory. Hardware doesn't like things being jumbled in memory. It wants nice, contiguous, compact things. Array list is better in this regard. The blue things, you can imagine those being the ints, and the array, at least in hotspot, is one contiguous piece of memory. And that's good. When you load the first element of that array, a cache line on x86 is 64 bytes. So you're loading 8 or even 16 ints all in one go. That's really good. But it's better. We're just going through this thing in order, right? We're going memory offset plus 0, memory offset plus 4, memory offset plus 8, memory offset plus 12. Guess what? The hardware can guess what's coming next. Memory offset plus 16. And so it will see this, and it will actually start prefetching the next cache line into memory, or the next cache line into last level cache. And so you will always hit the L3 cache, more or less. With the linked list, you could wait 50 nanoseconds to go out to main memory. This, you'll wait 5, maybe. Probably less. Much more predictable. But we're still having to go off into this other part of memory to get the objects. We can do better still. If we used an integer array, well, then you can kind of imagine the data looks like this. The data is just in the array. And that's super simple for the hardware to deal with, and your performance is much better. Obviously, there's less to garbage collect. Everything is good. If we could get value types and do generics over value types, that would be awesome. And again, everything here is order n. But clearly, there are some performance differences. In fact, linked list has a curve that doesn't look order n at all because of the effects it's having on the memory subsystem and memory accesses taking variable amounts of time. Okay, before we move on from lists, I've got a list of strings, and I want to turn it into an array, either of objects or strings. Which do you think is the fastest way? List to array with a new object array of size 0, or I should size it properly. What do you want to guess? Well, if we used find bugs would tell us we should definitely size the array. Okay. Let's just see what the benchmark results actually say. Okay, first off, string arrays are a lot slower. Like, a lot. Threefold. Why? Well, to answer that question, you have to understand this piece of code. Object array objects is equal to a new integer array. Objects 0 equals foo, the string foo. Does this code compile? Yes, it does. What happens when you run it? It raises an exception hopefully most of you have never seen, an array store exception, which means, I'm sorry, we have an integer array here. Why are you trying to put strings in it? But this is done through runtime checking. So every assignment to an array potentially has an extra bit of type checking associated with it. And yeah, that gets expensive. But of course, the object array is kind of special. If we see that our array is an object array, which objects are not objects? None of them. So we can make that cheaper. And in fact, that's what is done. So when we're copying the contents of an array list to an object array, we can safely get rid of all those checks. But when we're copying to a string array, we have to check every single element as we're doing it. And that's where the overhead is coming from. But findbugs was also wrong about the sized elements as well. You can actually see that toArray on a sized array is ever so slightly slower than the unsized or just not having an array at all and letting it create one. And the same is actually true for strings. But come on, I created an array of the right size for you. I mean, I tried to make this easy. Why would that be slower? Well, it depends. If you give me an array, you've already constructed it, and you've already had to zero allocate it, or zero initialize it. But if I create the array, if you give me an array that's too small, or you just don't give me one, then I can do a malloc of the array, and then technically, yeah, sure, I'm supposed to zero initialize it, but I'm just going to copy over that immediately anyway. So then the just-in-time compiler can go, well, I don't really need to zero it. Let's just copy over it and we're done. But if you give me some array, I don't know what state it's in, then I have to worry about all this. I don't get to have that. So, that's where the difference comes in. It's really unintuitive, but that is the case. Not that it's a big difference, mind you, but that is the case. Okay. Let's take an integer and convert it to a string. Integer toString, concatenation with the empty string, which really, I don't know, it offends me somehow. I just don't like the way it looks. But, okay, that's an option. Or I could use a string builder. Seem pretty good to me. Well, first off, I didn't actually tell you what num was. You probably assumed it was a static final because I made it capital. That's a good assumption. But I didn't make it a compile time constant. I made it a runtime constant that's actually random. So we're not going to be able to pre-compute anything at compile time. And then we run this thing, and we find out that builder is the slowest. And that just seems a bit strange to me, because if you know what concatenation compiles to, it just uses a builder. How did a builder beat a builder? The actual bytecode for the builder, as I wrote it, was something like this. For concatenation is this. If you're not liking bytecode, the Java code would be this. So we do new string builder, append quote quote, append num. It's a very logical transformation from the concatenation. Okay, but what did I do? I created a new string builder. I just appended num to it, and I called toString on it. I think I did less. Why did that run slower? Okay, well, let's try a straight-up comparison of these two. I will write that code manually, the same thing I should get from concat, and I will compare it to what I wrote before, and we'll see if we still see a difference. Yes, there is a difference. And then if I write the code that but the concatenation-like one, okay, it's like concatenation. Weird. Really, really weird. What happened here? So the VM has a very specific optimization that knows what concatenation looks like, and it goes and looks for that. But it only recognizes very specific patterns. Don't add a local variable. That will confuse it. It will recognize a very specific pattern, and it will optimize that pattern and that pattern only. Basically, what you need to understand is compilers are basically glorified regexes. All we do is pattern match code, and then we go, okay, well, I can replace it with something a little bit faster still. Now, I assume all of you have had to write regexes at some point in your life. You had some log file you had to churn through, and you wrote some regexes. And then you got your second log file. Did you handle every single case correctly? No. And could you debug your regex? No. That is what we have to deal with. So what did we do when we first made this regex, so to speak? Well, we took the input we had. We took a lot of your Java programs, and we said, well, a lot of people seem to be doing it that way. Let's make that fast. Excellent. And then the other person comes along and they wrote it a little differently. Whatever. And that's sort of what we do. Like, even if we knew this ahead of time, we'd go, well, if I do this thing for that guy, for those 9 people over there, I'd make it better for 9 people. What about that weirdo? Well, he's weird. So if you think you're getting clever and you write intricate, special-looking code, be prepared for special treatment. No, I did not say good treatment, I said special treatment. Now, let's take num and turn it into something that is actually a compile time constant. I'm going to say it's 1 shifted to the place left 20 times. And this is the result you get. Okay. Well, we learned before 3 nanoseconds is about how long it takes my laptop to return something. And that is, in fact, what happened here. That is all that is going on. If we go and run Java P and disassemble this, we'll find out that the actual bytecode of concat now is return the string 1,048,576. And that is it. How did that happen? Well, even Java C, which is a deliberately dumb compiler, does about 5 optimizations. Fortunately, it only needs 2 to pull this off. So we take 1 to the 20th, shift it to the left 20 times, and we go, well, that's a constant, a binary operator, and a constant. It's basically a regex. I can compute that. Okay, great. Num is really 1,048,576. All right, now we take num, and we go, we have the constant string, empty, and a constant number, 1,048,576. Let's, again, constant fold those. And now we end up with 1,048,576 as a string literal, and that's it. Brilliant. Produces code, just runs instantaneously. It'll actually run instantaneously in the interpreter. But you can see that performance doesn't entirely compose intuitively. A seemingly small change, not even changing whether the variable is static and final, but just changing its right-hand side, very dramatically changed the performance outcomes. And now, no matter how I wrote the builder manually, it's not going to do as well as concat. So concat is always the right answer. That's the takeaway, right? No. No, can't be that simple. So now let's take a string, and we're just going to add concatenate all the numbers up to 100. Why? I don't know. I felt like it. And then I'll try it with the builder as well. We're going to give the builder another chance. And what happens if we run this? Well, the builder wins. Comes in at 980 nanoseconds to concatenates nearly 2,700. So the builder is faster by a factor of 3. That looks pretty good. Oh, it gets better. Think about what happens when you do use a string builder or do a concatenation. What it actually translates to is create a new string builder, which has a character array inside of it, copy all the characters from the string we started with into that character array, add a little bit on the end, now call toString, which has a string and another character array. Oh, and by the way, copy all the characters again. So we create 4 objects for that concatenation operation. If you chain them together, it'll do a little bit better, but nominally it's 4 objects. So I used another tool called Caliper from Google to actually measure the object allocations, not just the performance. So concatenation produces 400 objects, and a mere 72,000 bytes of memory are used to produce a less than 300 character string. Well done. The builder generates 9 objects. You might think, well, shouldn't I just have like a string builder, a character array, a string, and another character array? Yeah, but the character array the string builder started with was a little too small. It was 16. And then it grows exponentially to 32 and 64 and 128 and 256, and ultimately ends up at about 512. to accommodate our 300 characters. So we create an extra 5 character arrays we don't really need. But we only use 1,640 bytes of memory. That's not so bad. But there is something there. I can actually tell String Builder how big I want it to be. And I know roughly how big I need it to be, 300 characters. So if I did that, performance improves a little bit, not a lot. But now we're down to actually just 4 objects and 1,464 bytes. OK, that's looking pretty good. Now, admittedly, for most of us, this just doesn't matter. I told you one of the things I used to work on was genomics applications. When you have strings that are 500,000 DNA nucleotides, this does actually start to matter. And in fact, this is true for all of our collections. We could actually just size them appropriately. Most of them start at like 16 for hashes, 10 for linked list and vector. String Builder and String Buffer are honestly the only ones I think are probably a little too small because they are size 16. And we tend to produce strings that are a bit bigger than that. But fortunately, the concatenation optimization, when it works, usually makes that kind of a non-issue. The rest of the time, we usually use small collections, and these sizes are OK. But there's one here I really do actually hate, vector. Now, you probably thought it was vector, but you probably thought it was because it's synchronized. Now, I don't care about that. That's not the problem with vector. No, the problem with vector is it doesn't grow exponentially. It grows linearly. So think about that for a second. If you're doing an append loop and you haven't sized it appropriately with most of these collections, you thought you wrote something that was order n. What you actually wrote was something that was in log n. Every log n steps through, we have to do an order n copy of the backing array. With vector, no, it grows from 10 to 20 to 30 to 40. So what you thought was order n is actually n squared. Brilliant. Yeah, that will hurt. But hey, you can actually set the growth size, so that's something. And now for our last example. Java is dynamically dispatched. There's no getting around it. By default, it is dynamically dispatched, and we need to optimize for that. And so, which do you think's better? Do you think if I have an object invocation and there's one type flowing through it, it performs better? Or there's an object invocation and there are 2 different types flowing through it and it performs better? Or there's an object invocation with 3 different types flowing through it and that performs better? You can probably guess what the right and wrong answers to this are. I've made it kind of obvious by saying that we say 3 types is megamorphic, which is basically we gave up. But let's try to demonstrate this. I can guarantee you there is a cliff at 3 types, but let's try to demonstrate this. The reason I say there's a cliff there is because I know what the machine code it produces is. If there is a function apply, so to speak, and there are 2 types flowing through it, or less than 2 types, it will expand into, say, an if-else of if the type is square, well, let's just inline the body of square apply, which is, x times x. Or if it's a cube, let's inline that and just do x times x times x. Else, we do something else. Versus, if it's more than 2 types, I can tell you it just calls function apply, and it has to do a dynamic lookup. OK, let's try to actually benchmark this. The setup for whether this one's a bit complicated. I've created an array of integers, actually in the static block of the benchmark. And then I call setup. And setup has a morphism that is parameterized like we saw with range before. And we go through and we warm up the benchmark code with different types of function objects. If morphism is greater than or equal to 1, we use square and we warm up the benchmark code. If it's greater than or equal to 2, we also do it with cube. If it's greater than or equal to 3, we do it with a cleverly named class called another square. And if it's greater than or equal to 4, we do yet another square. And then at the end, regardless of how many types we've shown it during the setup, I just use a square. So at the end of the day, we're just going to use one type. It's all about how many types did we show it during the setup phase. And this should actually change the code gen. And we'd kind of expect to produce a different performance result. But in fact, it doesn't. 3 and 4 look just as good as 1 and 2. But I thought like we inlined the code if there were less than 2 types, and otherwise we did a dynamic call, and isn't that slow? No, on a modern x86, that isn't slow. It will actually see that dynamic call, and because I'm only using square at the end of my test, it will go, oh, well, you're just always going to square. This is easy. I can predict where you're going to go before you even know it. And that's what it does. It prefetches what it needs based on predictions, just like with the if before. And so you can't see the difference. On an ARM, you could probably see the difference, but on an x86, you can't. Or can you? What happens if I put this inside of a loop? That worked for concatenation. Let's try it here, too. OK. Changed my test a great deal. It is now this. Call loop. Sum all the values of the calls over the nums. That's it. The setup is otherwise the same. And this is what you get. Huh. Apparently 1 is actually the best. You probably guessed that correctly. 2, not bad. I mean, it goes from 4,000 nanoseconds over this array of like 1,000 ints to 6,000. But 3 and 4, yeah, there's a cliff there. What actually happens is the call is left, when the call is left inside of a loop, it doesn't slow the call down per se, but what it does do is destroy the loop optimizations. And so you can't evaluate performance in isolation very easily. You can't go, oh, I wrote this benchmark to see if the call optimizes and go, 3, 4, 10 types look great to me. Yeah, that doesn't quite work. And even if you hadn't used just one type in the end after you'd warmed it up with a bunch, the numbers for just varying it would have looked a lot better than the numbers for putting it inside of a loop. Performance doesn't compose in obvious ways. You can take 2 things that are fast and put them together and get something that's slow. And that makes reasoning about performance quite difficult. Unfortunately, performance is just full of surprises. It's often not intuitive. It has all these intricacies. It has these sensitivities with these weird cliffs, like the huge method limit. It's not additive in a way that makes any sense to us. It's really, really hard to reason about if you don't live in this every day. And I'm guessing most of you probably don't want to. But I don't want you to be too doom and gloom about this. What I actually want you to see is, I just want you to write clean code. If you write clean, like tiny methods, you write code in the way that most people write code, we're probably going to optimize it pretty well. You know, if you start behaving like a crazy person and produce methods that have 8,000 bytes of bytecode in them, you've gotten what you deserve. Don't do that. We will generally take care of you. Yes, there are some weird cliffs, like the 2 types thing. And that sounds terrible. But you know what? We looked at it. 90% of call sites, even if they're the dynamic call, you want to guess how many types they use? 1. Another 5% use 2. And that's why we give up at 3. It's just like, well, we covered 95% of cases. That 1 in 20 guy, the hell with him. We did actually add support for 3 types to our VM, so if you're one of those people, come to us. It's really not so bad, but you do have to be careful. When you are pursuing performance things, it's very easy to mislead yourself, to write a test in isolation that you think shows you something, but unfortunately it doesn't. Oh, and let's all agree this is the best way to add the numbers from 1 to 1396. Because this is the fastest, right? Okay, we could have done this. That might be better. A little grade school arithmetic might actually be a better result, and yeah, that optimizes no matter how big your number is. Okay, I hope you found that fun. I hope you found it interesting. If you want to learn more, I would welcome you to look at these references. Alexei Shipolov is the guy who created JMH. He's done all sorts of performance blogging. I have lots of footnotes to far more detailed explanations of these things from his blog. Absolutely go look at his stuff, if you're interested in it. The Java Specialist newsletter is also a great reference. Psychobonic Lobotomy Saw is the blog of my former colleague, Nitsan Wakart. And Mechanical Sympathy is a blog that talks a lot about Java performance, but also low-level hardware performance, as the name might imply. So thank you all very much for coming. I hope you enjoyed it.